Alright, so got one more kind of topic to go through before we kind of finish out the material we'll go through before the exam. So, where are we at? So scroll down here, kind of have all the data files that we'll use this week. We'll be kind of using this new do file called MLR inference. So this is going to be multiple linear regression inference. Kind of what we'll talk about today and then on Thursday's class as well. I also put up those sample questions. So after class today, I think we should have covered everything that we would need for that next quiz. So you'll see that next quiz pop up this afternoon once I get back to my office. I would likely not start taking it today because we're just going to continue to go through more examples of what we talked about today on Thursday, as well as rehash some of the other stuff we've talked about with multiple linear regression. So although I'll post it today because I know everyone's schedules are different, I think if you're attending Thursday's class, that's going to help make that quiz a lot easier as well, right? I'll have that set to be due at the end of next week. So you'll kind of have all of next week to the end of the day, Friday, to do that quiz. Start studying those sample questions. I'll also put up the next problem set. So there, I'll kind of have that to be due not until the Tuesday before our exam, which is on October 17th. So that Tuesday is what, the 15th? So you have a lot of time to work on that third problem set. You know, I know that state is new to a lot of us. There's been some issues with people. I don't know, you know, I think I'm being clear in class, but you know, we operate in Stata, you know, and open up programs, right? I can use the interface, but anything that gets done here, this doesn't get saved anywhere. I don't want you taking screenshots of this and uploading it for the problem set. What should you be uploading for the problem sets? A do file, right? So we have this do file editor where we save all of our commands so that we don't have to worry about like, oh, if I make a mistake, now this is going to be in my screenshot and I've got to sift through all this stuff to see where did you do things right, where did you do things wrong. We should be saving all of our commands in here, and then either using comments to identify from the Stata output what the correct answer was, or kind of putting those, identifying those in a Word document separately, right? You know, and I've modeled the do files that I'm posting every week in a similar way, where we kind of have our code. I then might say something about what statistic we're grabbing from that output that that code gives us. This is kind of the procedure you should be using in Stata, saving all your code here, running it from your do file editor. This is what gets saved and what you can upload. Okay, probably talking to the wrong group for those of you who are here, but that's, you know, let's make sure for the third problem set and iron out any of those issues. So I extended the due date on that second problem set. I posted an announcement up after class, or it might have been on Friday actually when I say that. So a few more days to work on that second problem set. The due date's now passed. I'll kind of start getting those graded. So you'll see your grades start being influenced by that. I also have it set now. So these in-class quizzes are just going to be kind of extra credit. Now, here's like the original one I had in class. I scaled it because I think the question I asked was just like 2 points. So this is kind of what the number of points you would basically, if you were in class that day. You got the full 5 points. But I've got it set now that the only thing counting towards your grade on Canvas are your quiz scores and then your problem set scores. Right? Now, obviously, this one hasn't been graded yet, so it's not influencing your grade until it gets graded. But these are what gets added in at the very end of the semester to your grades. They're just extra credit points. Okay. So then we'll have a third quiz and a third problem set that'll be turned in before you take that midterm. I think, you know, after this week, basically all of next week, and then that Tuesday before the midterm, we're basically just going to go through more examples in class. We'll have these, you know, these practice problems. Oh, I already switched the page. Hold on. We'll have these practice problems, right, to kind of work through. Not only, you know, the first, the second, and third set. So if you have any questions over any of those, you can kind of bring those questions to class on those days. I'll also be getting up a practice exam. I probably won't get that up until tomorrow. I want to go through it a little bit more to make sure it's going to be as representative of the types of questions that I'll ask you on the exam as possible. So I've almost got it ready to go. So you should see that pop up probably tomorrow afternoon as I'm working on things, or possibly in the morning. And we'll kind of, you know, go through a lot of those problems in class as well. It's basically just going to be trying to set us up to do really well on that midterm, because I know that the first midterm is kind of tough, but that final is a lot more difficult, right? We start touching on a lot more difficult concepts. So I want to make sure we kind of put ourselves in a good position after this first midterm so that the final isn't as scary once we get there, okay? Any questions for me before we jump into things here today? Okay, I think that should be all the housekeeping stuff. So let's go here. And I'll keep going. So up to this point, what we've talked about is being able to determine if there's statistical significance on just one slope coefficient, right? So we had those p-values that Stata gave us. We kind of test each individual variable to say, does it have a statistically significant relationship with our y variable? What we're now going to do is thinking about comparing models, right? And also thinking about something we'll call joint significance, okay? So we know that as we add in more of these independent variables on our right-hand side, our R squared is definitely going to be going up, right? At the very least, it could maybe not change at all. But, you know, if we're looking out to like even the 100th decimal, adding in a variable should increase our R squared infinitesimal amount at the very least, right? So, you know, does our new model actually do a better job of predicting? Just because we have a higher R squared, what's one measure of model kind of predictive power that we talked about? It's a little bit different than the R squared. We penalize ourselves for adding in more variables with the adjusted R squared, right? So this was the idea. Once again, I'll probably rehash and revisit some topics here throughout class today. So we said our R squared would typically just be 1 minus. So our R squared represents the proportion of the variation that we can explain with our model. So that would be the same as 1 minus the proportion that we can't explain. Now, our adjusted R squared, we said this amount that we can't explain, we want to scale it up by a certain factor, which was this will always be greater than 1. So if I'm multiplying this by something, I'm always going to be subtracting a slightly larger value. So my adjusted R squared will always be a little bit less than my R squared. So this was kind of our first thought of, you know, I'm looking at multiple variables there that I'm adding on the right-hand side. I don't want to just rely on a statistic that doesn't account for that. So I'll use the adjusted R squared instead. Okay. So that was one way we could look at and see, is this model a better predictor than the other, right? Is the adjusted R squared larger or smaller? We have a slightly better way of doing this, which is kind of using a joint hypothesis test where we're thinking about, we have a restricted model. So it's going to be a model, this one's very basic, but I've only included one variable, right? The unrestricted model is I have these other 2 variables in my data set, and I'm going to include those into my regression as well. Now, automatically, I know my R squared is going to be higher, right? I know that has to be larger, but we're going to do it's kind of like, we're going to test to see, is that change in the R squared, this isn't quite theoretically correct, but is it statistically significant? Was that change in our R squared statistically significant? Or adding in these 2 additional variables, can we say with 90, 95, 99% confidence that we've actually increased the amount of variation that we're explaining in our Y variable, or that we've actually increased the R squared? Okay. So, I mean, it does, we have actually increased it, but can we say that adding in these models had a statistically significant impact on our predictions? So our joint hypothesis test is going to look similar to just our individual one, which is we start out assuming that the coefficients now, instead of just one coefficient, we assume that both of them, for these variables that we added in, when we added it in simultaneously, we'll start out assuming they're both equal to 0. That adding these 2 variables into our model, neither one had any predictive power. If we can reject that, well, then we're saying, adding in these 2 additional variables, we actually are explaining more of that variation in Y at a statistically significant level. Okay. So, okay, let's turn that on. So, just like with everything that we've been doing this semester, like if we want to test for something, we always start out assuming the exact opposite is true. Okay. So, right, how do we run this test for both of these estimates simultaneously? Well, we kind of have a problem. If we were to think about when we do this test for one coefficient, and that was like we were saying, okay, the distribution of these slope coefficients. We have a sample size over 30, should be normally distributed. Even if we assume that there is no effect, if that in fact is the case, so we assume there's no effect, let's say somehow we get the population data and we can see there, yeah, that slope estimate with the population data is 0. Even if what we assume to be true is in fact true, from our samples, there's going to be a likelihood that we see something more than what we'll do here is 1.96 standard deviations away from that value of 0, right? And we will end up rejecting that null even though we shouldn't be. Or we'll be making type 1 errors. What represented our type 1 error? Alpha. So here, these standard normal kind of approximation values of 1.96 goes with an alpha of 0.05 because we have the two-tailed test here, right? Equal to 0, so we've got two tails. So we have half of alpha in each tail. We look up that area of 0.025 in our standard normal table. Sure enough, we'll find that 1.96. Now, here, alpha represents the probability I'll make a type 1 error, right? 0.05. If I think about then, what's the probability I make a type 1 error in my determination of is that first kind of test statistic, or that test statistic associated with the first slope coefficient, is that in my rejection region or an absolute value, is it greater than 1.96? And is my second variable that I've included, is that slope coefficient also greater than that critical value? Well, anytime I'm trying to find the probability of A and B, how do I find that probability? It's the probability of A times the probability of B, if we assume they're independent and there's no intersection. Right? So if I do that, I would have 0.05 times 0.05. That's going to be 0.025. That's not my desired type 1 error. The type 1 error I wanted was 0.05, the 5% significance level. So we can't simply just test each individual test statistic and then multiply those probabilities because it won't quite be the right value. In fact, it's going to be half the right value here. Right? So that's not our desired type 1 error. So what are we going to do? Right? This isn't going to work. Scratch off this. Right? So just like we were using student t distributions, we've got another distribution that we can rely on, which is the F distribution. Right? So student t distribution was still when we were assuming it was equal to 0, and we could see things on the left or the right. The F distribution is a little bit different. So if I think about, I want to test a model where I've included 2 additional variables. I know that this R squared is always going to be higher. So when I find the change in that R squared, it's always going to be a positive value. So essentially, I know that when I'm testing whether or not my unrestricted model is better than the restricted, I'm always going to be having a positive change in R squared. So when I turn that into a test statistic, I'm only going to ever see things in the right tail. So for these F distribution, these joint hypothesis tests, even though we're assuming that they're both equal to 0 when we add these in, the real test that we're doing is whether or not there's a statistically significant change in our R squared, in which case that can only ever be positive. Adding in more variables can only ever see the R squared goes up, never negative. So with the F distribution in this joint hypothesis test, we're going to be looking at a right tail test, right? We're always going to only be looking at the right tail now. Okay? So why? Well, because we know that it has to be increasing our R squared. To be more precise, how would we calculate the test statistic for that change in the R squared? So I'll show you this way first, and then there's a more friendly version. So this is kind of really what we're doing, and it really lines up with what's going on behind the scenes. So this SSR, I just wrote it in a slightly different format to kind of keep some of the letters a little bit more clear. So here is my restricted models, sum of the squared residuals, or the residual sum of squares. Here is my unrestricted models, sum of the square residuals. So basically these represent the proportion, sorry, not proportion. These represent the amount of variation that I can't explain in my Y variable. So the amount of variation that I can't explain in my restricted model, right, is always going to be a little bit higher, right? When I include more regressions, the amount of regressions, when I include more independent variables into my regression, the amount that I can not explain is going to go down. So this difference will always be positive. It's the same idea as if I'm really testing for the difference between the R squareds. I know the R squared of my unrestricted model is always going to be a little bit higher. I'm always going to be able to explain a little more of the variation of my Y variable. So we'll hold on to this for a second, but don't get too lost in this because there's a better version that we can use for our test statistic. But this is really what state is kind of going to be doing behind the scenes. It's using those residual sum of squares from our unrestricted and our restricted model. It's then going to divide that difference in the numerator by Q. So what Q is going to be here is the number of variables we're leaving out of our restricted model. So we go back here, what would my Q be? So I'm comparing that unrestricted model to my restricted. The number of variables I left out was 2. It's not a trick question, right? Just that x2 and x3. Now there's another thing, just like we had with our adjusted R squared, which is K, which is going to be the number of independent variables included in the unrestricted model. So what would my K be here? How many variables did I include in the unrestricted model? 3. We don't count the intercept, right? It's not a variable. We always think about the intercept. It's like a starting point, right? It's the same for every observation. The variables that we've included are just these 3. Okay? So, oh, there we go. We've now got Q, got K, right? We know how to identify those. We can, from stata output, start to calculate this F statistic. So, just a couple more notes about the F distribution. And I forgot to pull it up, but I'll pull open the file that I put on Canvas that has the actual F table, right? But just like the student T distribution, the F distribution has degrees of freedom. So we didn't hammer on this too much. But when we went back early on the semester talking about the student T distribution, it's not distribution, it's distributions, right? Every different degrees of freedom has a slightly different student T distribution. We said what characterizes these student T distributions is the sample size -1. That was our degrees of freedom, okay? So as that sample size went up, we said that student T distribution got closer and closer to a what distribution? We had a truly infinite standard normal distribution. Yep. So with an F distribution, it's going to be not only do we have 1 degrees of freedom, but because we're not dividing just by n-1, we're dividing by n-k-1, and then we're dividing by Q here, we actually have 2 degrees of freedom. So our degrees of freedom are going to be, well, we're dividing by Q and we're dividing by n-k-1. So those are going to be our 2 degrees of freedom. Now in practice, and I'll show you what happens if this isn't the case later on today, but our sample sizes are usually so large that second degrees of freedom, and when we look at the table, we usually can go all the way down to that last row because anything over 200, we approximate kind of with an that infinite row. Now, technically, there's F distributions for every single n-k-1, but by the time we get to that 200, out to the 3rd decimal, it doesn't hardly look any different. But this first degrees of freedom, this will be quite different, right? Sometimes we'll be leaving out 3 variables, sometimes we'll be leaving out 8, right? So that one's going to matter a lot more. So let's actually pull open this F table. I put the file up on the main page on Canvas as well. Oh, it's thinking. Well, while we're waiting for it, actually, cancel this. Okay. Let's download from Canvas. Open it up this way. So here's kind of our F table. We've got 2 degrees of freedom. So for us, I think if we didn't have a sample size, but let's just assume, because I think the example I'll show you here in a second, the sample size is like 1400. So our n-k-1 is going to be well over 200. We'll use this last row as kind of our approximation, right? Anything over 200, we can just use that infinite row to kind of approximate. Now, what was our Q, or our number of degrees of freedom in our numerator? So remember, when we were calculating that F statistic, Q is what was in our numerator. So 2 would have been Q. So we go down here. The F value for the F statistic that would give us, now this table can only ever tell us 1 type 1 error or 1 alpha value. So it's always going to give us the critical values for the alpha of 0.05. So for us, we've got 2.996. So what this is going to look like, and I'll look up some visuals of the F distribution here in a second for you. But I can draw one out for you here. So if we're thinking about what an F distribution looks like, it's not symmetric. In fact, we know that the change is always going to be positive, so we have like a longer right tail. So we just looked up for our degrees of freedom, the critical value associated with having an alpha of 0.05 in that right tail was 2.996. Okay. So if I see a test statistic from my data, right, and you actually calculate the F value based off of the restricted and unrestricted model, anytime I see an F statistic out here, what's going to be true about my p-value? It's going to be what compared to alpha? The area to the right of 2.996. If I start to look at higher values, what's happening to the area to the right? It's getting smaller, right? So I know that for any F statistic that's to the right of my critical value, it's the same kind of thing we're doing with old hypothesis testing. Anytime I see a test statistic, it's just now that test statistic is coming from an F distribution. Anytime it's to the right of that critical value, my p-value has to be less than that alpha of 0.05. So as we get larger and larger F statistics, that's going to result in smaller and smaller p-values. The smaller my p-value, the more likely I am to reject. So same kind of principles apply to what we've been doing, just looks a little bit different. In fact, kind of notice here, it's got these long right tails. These are just a different, they called it N and M. We're using Q and K because it's specific to regression. Right, it changes the kind of the shape of our F distribution a little bit, which then the same value, like of 1, the area to the right of it would be different for different combinations of these degrees of freedom. So I'm probably not going to have you use this table a lot when it comes to like asking you. I'm not going to make you use it when I ask you questions on the quiz or on the exam. I'll show you some data output that I would be more likely to ask about, but I would maybe ask you to calculate the F statistic, right? We have that equation. We want to think about what that test statistic is really telling us, which is the number of standard deviations away from that assumed true value, assumed true coefficient of 0, that change in our R squared was.
So for the second degree of freedom, like how far above 200 do you go into the one?
Well, in practice, I mean, you know, it's not really going to matter unless you have a test statistic that falls in between these two, right? Because you make the rejection decision. Like if I had 3.5, I'm going to reject it no matter if I use 200 or infinity. In practice, we can use Stata and they can actually use the exact degrees of freedom and we don't have to worry about kind of using this last row. And I'm not going to ever ask you a question where like, it's not going to be clear what you should use. If I ever did ask you a question, I'd give you like an exact value here you can find, but I'm not really focused on that too much. Okay. Yeah, in practice here, I don't know how much above 200. I mean, we're talking about being off at the second decimal here by what, 0.05. So I mean, probably want to be 300-400. By that point, we're probably getting a pretty close approximation using this last row. Yep. Any other questions before we keep moving? Right. So we just went through all of this. We talked about this. So we're back to our kind of initial hypothesis test, which is that adding in both of these variables at the same time had no impact, right, on our predictive power of our, you know, the model we're using to explain why. Or I should say more precisely, the model we're using to explain the variation in y, right? That was kind of what our R squared was picking up. So if we can reject this null, what we're really saying is that adding in these additional variables gave us more predictive or explanatory power, right? And that model will be able to come up with better predictions for that value of y. Okay? So how do we compute this, right? Well, I kind of showed you this original version, but there's a much easier, kinder version. So if I've got the residual sum of squares, you had to use this in the second problem set. Remember, there's some total variation that exists in the data. That's just going to be a combination of what our model can explain and what our model can't explain, the residuals. So anytime you would have like a residual sum of squares, you can always rewrite it as this, right? And in fact, if you start dividing by like the total sum of squares here, you can actually rewrite the residual of the total as what? 1 minus the r squared. So we can kind of play around with that. We're not going to really care too much about the math, but if we were to start to rewrite things, we can actually get a form of our F statistic equation that I think makes a little bit more sense, will probably make a little more sense to you originally or initially. So it's going to be the difference between our unrestricted models r squared, so that's the one where we included all the variables, and the r squared of the regression where we left some of them out. So it's going to be essentially like, what was the change in the r squared we saw from adding in these variables into our regression? We're then going to scale that or divide that by the number of variables that we included, right? And then down here, we're going to have 1 minus the r squared from the unrestricted model. So this is kind of like essentially the proportion of variation we couldn't explain with our unrestricted model. And then scale that or divide that by n minus k minus 1. So we're still like penalizing ourselves, and we're adding in additional variables on that right-hand side k, because our F statistic we have this new form, which was r squared of the unrestricted minus r squared of the restricted divided by q over 1 minus r squared of the unrestricted divided by n minus k minus 1. Okay? So let's think about if we are trying to do a test for joint significance of including, so here we were only including like 2, right? Well, as I start to have more variables in my regression, what's that going to do to my F statistic, right? So let's just think about a regression where I have just more variables there in my unrestricted model. It's going to increase k, right? What's that going to do to this? If I'm subtracting a larger value, if I'm decreasing the denominator, what's happening to this fraction? If I'm increasing the denominator, what's happening to this fraction? So by including more variables in my regression, what's happening to my F statistic? It's going down, which means my p-value will be doing what? Going up, which means it's less likely I can say that these added variables have an effect. Now, this is just if I have more variables in general. So this could be impacting both the restricted and the unrestricted model. If I just simply am thinking about, okay, what if I want to make a joint hypothesis test, but I don't want to do it for just 2 variables. I want to do it for 3 or 4 or 5, right? I want to run a joint hypothesis test for a larger set of variables. What's that going to do to my F statistic? Well, my Q is going to go up, right? Now, if I've got more variables I'm testing the joint significance for. So what's going to happen to this fraction? Denominator's larger. It's going to go down. If I now have a smaller numerator, what's happening to my F statistic? It's going down. My p-value is going up. Less likely I can reject the null. So testing a higher number of significant, like joint significant variables, or just having more variables included there on my right-hand side is going to give me a lower F statistic, make it a little bit less likely I can reject the null. I'll try to show you this with the data here later on. Yeah.
So if we're like graphing that F value, would you kind of like say that F value is like a critical value, anything to the right that I can reject?
Yeah, so we want to be careful. The critical values would be what we kind of find from that table that tells us what would give us that threshold cutoff significance level of 0.05. The area to the right of our F statistic that we're calculating this difference in the R squared, that area would actually represent what? So if we have a test statistic, the area that's more extreme than it, but under the curve, that should represent our p-value, right? That p-value is the probability we saw the test statistic we did or anything more extreme. Now, before we had to look at that area, multiply it by 2 because we had a 2-tailed test. Here, when the R squared, we know it has to go up and we only have a right-tailed test. So it's just that area in the right tail as our p-value, okay? So that was this idea, right? So here, this was my first test statistic. Here would be my p-value. If I change one of these things such that it's lowering my F statistic, what's going to happen? What's happening to my p-value? Has to be higher, yeah, so it's be like. P-value 2, I guess, and this we would call it p-value that was associated with the first one. Yep. Any other questions on that before we keep moving? Okay. All right, so let's look at some actual results from Stata, and then we'll kind of dive deeper into the actual D file, right? So let's say I was trying to predict GPA in your first year of college. I've got age, high school GPA, and an identifier for whether or not the individual is female, right? So I run this regression. I don't know. I decided to throw in the robust command just to remind ourselves, what is that robust command control for? So we tested for something in our errors, and if we could reject the null, we said we should use this robust command to account for the fact that our errors might be heteroscedastic, right? I must have known that these were, and so I threw it in there, right? But it doesn't really impact what we're going to be doing, but just to kind of rehash some of these old ideas. Now, if I look at just the individual statistical significance of each one of these variables, I would say that which of them could I say have a statistically significant impact on college GPAs in year one? I'm looking at those p-values. So can I say that age has a statistically significant impact? Has a p-value of 0.006. That's less than 0.1, 0.05, and a very strong statistical significant effect. What about high school GPA? Well, the p-value here is 0, right? So yes, I definitely can reject them. Female, 0.00. Yes, so I can reject individually. I found that each one of them has a statistically significant impact. Now, just to kind of revisit some old things, what if I didn't give you the p-values or the test statistics here? What could I use to make a determination, at least at my 95% level, or at the 5% significance level? So if I look at those confidence intervals, what has to be true if I reject the null? Remember, the nulls, we start out assuming each one of these slope coefficients is equal to 0. So if I reject the null, what must be true about my confidence interval? It doesn't include 0, right? Because my confidence interval is telling me at the 5% significance or 95% confidence level, here are the possible true values for that slope coefficient. If 0 isn't in that range, then when I do a hypothesis test for 0, I'll reject it, right? Because it's not one of the possible true values, right? At least at this level, right? And kind of notice each one of these confidence intervals doesn't include 0. It either only includes negative or only includes positive values. Now, one thing I think people Googled, and maybe there was a little bit of confusion, but one thing that's kind of a pain in Stata, I can only, if I ask you to do this, I can really only ask you about 5% significance level, because Stata only ever gives us one confidence interval. Now, there is a command you can add in, I think it's level, and then in parentheses, what level you want. You put a comma and then that after your regression, and it will change what confidence interval it tells you. But if I wanted to test this against all three, that means I'd have to run the regression 3 times. It's as long as I've got the p-value there, it's probably a little bit more useful to use the p-value. But I do want to test this concept. So like on a quiz question or something, I might leave this out and kind of make a rejection decision based off the confidence interval I show you, right? Because we still want to kind of line up those concepts, right? Or I want to test you for whether or not you understand that concept. Maybe is a better way to say it. Okay, so that's getting away from this joint significance. That was just the statistical significance of each individual coefficient. So let's say instead, so we got here, thinking about this as our restricted R squared. Right? This is going to be like our restricted model. I'm then going to think about 2 additional variables. I move all this stuff away. I think this getting absorbed up there. There we go. So I now have this additional variable, which was the number of math science credits the person took their first year of college. That probably is going to impact your GPA. Taking a class like this probably isn't as friendly to your GPA as, I don't know. I saw someone on a transcript. I know I was in this class, but I had to do like a student athlete thing. They were taking billiards. I guess that's a class. So I'm probably going to have a slightly more negative impact taking this class than that one. So I've got the number of math science credits and then a 1-0 variable for whether or not they worked. Right? So I've added in two variables, so what should happen to my R squared? It should go up, right? So sure enough, what was it before? 0.1956, now it's 0.1997. So it didn't go up by much, right? So we saw that it went up, but can I say that adding these two variables in, that my model was making any better predictions, right? Or was I actually able to explain a statistically significant amount more of the variation in my Y variable college GPAs? Okay, because I know that adding things in, I can always increase the R square a little bit, but can I say that at a statistically significant level? So what are we going to do? Well, I've now got my R squared from the unrestricted model. I've got my R squared from the restricted model. Those were two of the things I needed in our equation. The other thing we needed was the number of restrictions. So what would that be here? So if we go back here, I originally included just age, high school GPA female. So my number of restrictions is 2. I have 2 additional variables there. What's my K? That's the total number of variables in my unrestricted model. So that would be 5. Okay. So I've got everything I need, and I need one more thing. My sample size. What's my sample size here? 1401. Right? So we talked before. I'll revisit this. So just for right now, we'll grab that sample size and then I'll try to remember what I want to go through next. I'll complete this thought first. So I've got my S-statistic equation. We just talked about, we can identify all of the components that we needed. Now it's just a matter of plugging and shoving, right? Plug in our R squareds, plug in our Q, plug in our N, plug in our K. We can kind of get our F statistic, which is 3.57. Okay, so if we think about before, if I were to look this up, what would my 2 degrees of freedom be? 2, and essentially we'd be using that infinite row, right? So we would have found the same exact value that we found before, which I think was like what, 2.996. So if I were to kind of plot this out, at those 2 degrees of freedom, my F statistic, we said the critical value associated with an alpha of 0.05 was that 2.996. We just found an F statistic using the actual sample data of 3.57. So can I reject the null? Well, is it to the right of my critical value? Yes. My p-value is going to be smaller than alpha. So I should be able to reject at least at the 5% significance level. But that table only gives me one level. I might want to be able to say what levels can I reject at? 10, 5, or 1% significance. So there, relying on Stata, we can be a little bit more accurate. Okay? Because Stata not only will tell us the test statistic, it will also report to us the p-value. Right? It had, there is like an equation. I didn't show it to you, like a probability mass function equation that you could integrate. So you're looking for the area under the curve to the right of your specific value. It basically Stata will do that behind the scenes for you, right? We don't want to have to deal with all the integration. So what will that look like, right? So here we're going to kind of cheat. We're going to go ahead a little bit and I'll come back to that statement. So there's actually a command in Stata after you run the unrestricted model. You can say, okay, I want to test the joint significance of these 2 variables. So that was the work variable and then that math science credit variable, right? That was what we were going to test the joint significance of. Then adding those into our model, were we able to explain a statistically significant more amount of the variation in our Y variable? Well, you'll notice, why is my test statistic a little bit off here? When I calculated in the previous slide, it was 3.57. Now I've got 3.7. Well, you wouldn't think it makes that much of a difference, but what am I doing here? I'm rounding to the 4th decimal. Doesn't seem like it would make that much of a difference, but when we're, depending on the size of the R squared, it can make a pretty significant, difference. So here, if I round to the 4th decimal, I get 3.57. Stata is actually using whatever the R squared is, like stored out to, I don't remember how many decimals, but I'm guessing it's at least 100, if not more, right? So it can be a little bit more precise, right? So it's going to give me a little more accurate, idea of what the test statistic is, and then can also give me that p-value. So here, with 10 and 5% significance, I can say that those added variables of math science credits and whether or not the student is working while they're in college has a statistically significant effect at that 10 and 5% level, but not at the 1% level. right? That model where it's unrestricted, adding in these two additional variables, I'm making better predictions essentially, right? I'm explaining a statistically significant amount more of the variation in college GPAs, that Y variable. Okay. So I think that's what I have kind of here on this last one, right? Any questions on anything here? So it's a lot easier to kind of use this p-value. We just have to kind of remember, what is our null hypothesis? Our null is that these added variables, these simultaneously added variables, have no impact, right, on our predictive power. So I'm going to get out of this, and then we're going to jump into Stata probably for like the rest of this class. So I think just seeing more examples is going to be helpful. So let's see, let's go up here. Our do file, I'm gonna make this a little bit bigger so things are kind of on the same line. So I'm just using that MLR inference do file that's on the main page of Canvas. The file that we're going to open up is this star public use. So I'm going to use my global. I don't know. I kind of like that. If you don't, you can always just go to File, Open, or go to your OneDrive. Once you download that star public use and then kind of drag it into your OneDrive, you can open it from here. Now, probably what's good practice, and here it's because I'm in a kind of a presenting or this trying to show you multiple things, so it kind of cuts it off, so it's kind of a pain. But everything here I said earlier, this just goes away later, right? So I might want to remember exactly what that file path and what the file was called. I'll just copy and paste that line of code. Now, if I have like a too small of a window, notice it'll put this on a separate line. So I'll have to kind of do that, right? But here, now I've saved kind of that command that I ran just based off of using the interface. Now, one issue you might run into is if I then go back and try to do this again, if I already had data open, well, it opened this one up, but it shouldn't. Why is it opening it up? It should yell at me because, let's see if I didn't clear anything out. So apparently it's acting okay. But if it's not, it's because it's the same data set. If you had a different data set open and you had made changes to it, it wouldn't be able to do that unless you tell it to kind of clear out the old data. Right? So now we've got our file open. I'm going to run this regression where we looked at here. I've just got two variables, so whether or not they were female and then kind of age. So I'm going to run that regression. I've got an R squared of 0.015, so pretty low. Right? And then I'm going to think about, all right, what if I add in kind of some additional variables here? Now I'm adding in quite a few, right? So I've got their GPA, so I think we'll rename this later on in the file, but this is basically a high school GPA. Whether or not they worked. Sometimes if you can't remember what variables are, a lot of these data sets, they'll download with the variable having a label, so that HCOM, I couldn't remember what it is. Oh, it's a 1 if they live at home, 0 if not. Then you've even got like, did mom and dad go to college? I think that's what the dad and mom too. So let's see, dad too. Yeah, father has a college or is a college graduate, and then that math science credits. So I've now included what? 1, 2, 3, 4, 5, 6, right? So I've got 6 additional variables in there. Okay. Now I'll kind of change this. I'll upload this again. I was using this for another example. I'm using it here to kind of do joint significance. This was going to line up with our Q, right? Our number of restrictions here, we had 6 variables in our second regression that we didn't include in the first, right? So what would my K be? So that's the number of independent variables in our unrestricted model. So what would K be equal to here? I've got these 6 variables I left out plus these additional 2, so 8. Right? Now I'm going to run this second regression in Stata. Sure enough, I've added in 6 more variables. What's probably happened to our R squared? Not only did I add in 6, one of them was high school GPA, probably a good predictor of college GPA. Sure enough, my R squared goes from 0.015 to 0.2. So a pretty large increase in our R squared, but in order to do so, we added 6 more variables. So when we're calculating that F statistic and we're doing these joint hypothesis tests, yes, even if we see large increases in R squared, it's likely that we're going to be able to reject the null. But in the calculation of that test statistic, we said if we're adding in more, that Q is going up, that's gonna cause the F statistic to be a little bit lower, right? So we can't say with guaranteed certainty. Give me 1 second. I'll be right back.
That's right, I do read walks out. Come on, he's a fucking commentator professor, you think he's gonna be perfect? That is great. I mean, so we can send about extend because the class will us be already for the class.
All right, well, I have to go. I don't, hopefully not yet, but I have to go take my wife to the hospital. So, what we'll do is I have the recording from my previous one. I'll post that on YouTube. Although, if I'm back, I should be back in class on Thursday. We'll kind of I'll pick up where we left up here. We've got a lot of the days for additional review. So 2 days next week are basically just gonna be review. That Tuesday before the exam is review. Thursday, I was gonna kind of rehash some of these examples anyways. So we should have more than enough time to kind of pick up where we left off and kind of go through this stuff. But really all we're gonna do the rest of this week is focus on joint hypothesis testing. If for whatever reason I can't physically be here on Thursday, I'll basically create a recording where I'm just going through exactly what I would have went through if it was here, and I'll kind of post that to that YouTube page. So I can let you know at the beginning of the semester something like this might happen. So I'll try to be as present as I can physically in class, kind of moving forward. But if I'm not able to, I'll kind of utilize that YouTube page. I can create these recordings day to day, so we'll have the exact replacements of class. I'll also kind of post, anytime during office hours, if you want to meet virtually, if I'm not able to be on campus, we can do it that way as well. Hopefully, fingers crossed, it's maybe is nothing, but I've got to go. So on Thursday, hopefully, like I said, I might be back and we will have another. I'm hoping I have another couple weeks because I was planning on another couple weeks. So, but if not, keep an eye on Canvas for announcements and I'll kind of get out as much information. That's going to be how I'm going to communicate with all of you. Okay. I apologize. Hopefully I'll see you guys on Thursday.
Get out of here. Thank you.
Get out.
Get out. Thank you.
Yep.